All right, so one of the things that's going to kind of be with us the rest of chapter 9, pretty much in every section, is a new operation. And somebody y'all probably heard of, right? It's hard not to get excited when you're talking about math, right? N reads as n factorial, and it comes. It's a symbol that's used because it shows it quite a bit in probability. N factorial is defined mathematically to be this: n times n minus 1 factorial. We call it a recursive definition. But what does that mean? That means it's n times n minus 1 times n minus 2 times n minus 3, all the way down until you get to 3 times 2 times 1. Okay. So in other words, an example would be like 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. We stop at 1 because if we went to 0, it would nullify itself out. So why is it so important? Well, it's actually defined to be the number of ways, we'll put is here, is the number of ways to arrange n items. So for instance, if you have like 3 books, right, and 1 shelf, how many different ways are there to arrange 3 books? You can have book 1, 2, 3. You can have book 1, 3, 2. You can have books, what would be another arrangement? Oh, 3, 2, 1, 3, 1, 2, 2, 1, 3, and 2, 3, 1, right? I think that's about it. Did I miss one? No? Okay, so how many is that? 1, 2, 3, 4, 5, 6 ways. So there are 6 ways to arrange 3 objects, okay? And so that comes out to 3 times 2 times 1, which we define it as 3 factorial. All right. Now there's an interesting caveat to this definition. We know that 1 factorial is equal to what? 1, right? So you can think of that as just being like, I'm excited about saying 1, and whether I say it excitedly or not, it's just 1 either way. We also know that 0 factorial is equal to what? You would think 0, right? But it's actually equal to 1 as well. Yeah. So what does that mean? That means that while 1 does not equal 0, 1 factorial does in fact equal 0 factorial. And so for the non-initiate who walks by, who doesn't know what factorial means, they might think that, hey, 1 doesn't equal 0 unless you say it with enough enthusiasm, right? Then if you believe, you know, that might makes right, then it does, right? Like Putin. Lincoln said, have faith that right, being right makes you mighty. Whereas I think Putin's like, if you're mighty, then you're right. Anyway, you can actually prove this with the recursive relationship, right? Watch this. 1 factorial by this definition is equal to 1 times 1 minus 1 factorial, which of course is equal to 1 times 0 factorial, and anything times 1 is itself, and you get 0 factorial. All right. So how is it then consistent with this definition? Well, if you have 1 book, how many ways are there to arrange 1 book on a shelf? Let me go ahead and build the shelf. Here's the shelf. There's only 1 way to arrange 1 book on the shelf, right? There it is. There's the book. Okay. So there's 1 way. What if you don't have any books? How many ways are there to arrange no books on a shelf? There's 1 way, right? And there it is. Beautiful. Okay. So n factorial, we typically define it for, again, natural numbers, starting with n equals 1, but it is defined for n equals 0. Now, for negative numbers, it's defined, you might, like there's a Wikipedia entry on how to do it for negative numbers, but that's just kind of getting into this squirrely region. That won't be on any kind of exam that we take. All right. Now, one of the things that's important about this recursive relation, and I'll add this here as well, is how we're going to simplify it later on. So if you see something like n plus 2 factorial, divided by n factorial. We can actually simplify this, okay? And the way we do this is we start with the larger of the two, which is the numerator, right? N plus 2 is bigger than n when n is a natural number. And we write it recursively. N plus 2 factorial is n plus 2 times n plus 1 times n plus 0, or n times n minus 1. But I'm going to stop right there. Why do I want to stop when I get to n? Because that's what my denominator is. And now what happens with your n factorials all the way down the line? All those factors will do what? They'll divide out. And so we're just equal with, we're equal to n plus 2 times n plus 1. Okay, so we're going to be simplifying factorials quite a bit. Here, you try this one. You try this one. You simplify n factorial all over n minus 3 factorial. Simplify it. All right, which one's larger, n or n minus 3? N, right? The numerator again. So you'll write it recursively, n, and just keep subtracting 1 times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5. But hey, I'm going to stop when I get to n minus 3 because that's what the denominator is. So that's right. Again, you could say like you tie off the recursive pattern with a factorial. And now that those are the same, they're the same all the way down the line. And of course, you're just left with what's left. Okay, so we'll be doing that quite a bit in this chapter. Okay, fantastic. So let's go ahead then and determine, based on what we did yesterday, determine whether the following sequences converge or diverge. All right, so here's the sequence: 1/2, 2/3, 3/4, 4/5, comma, dot, 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 comma, n over n plus 1, comma, dot, dot, dot. Now, again, it's nice that we have this right here. What is this called right here? Two names we gave to it yesterday. Okay, what was the second one if you can't remember the first? I'm going to sit over here. The nth term. Yeah, the nth term. This is the nth term, or the rule of sequence. Yeah, rule of sequence. Rule of sequence. And boy, that's really helpful to have, right? That's helpful to have. That's what I call the Holy Grail. So if you want to know if the sequences converges or diverges, essentially, we're looking at the same limit each and every time. This is how you show your analysis. You take the limit as n goes to infinity of the nth term, right? So it'll always be this. And then you just evaluate it based upon what we previously did. What does this go to? N to the first, n to the first. So it's leading coefficient over leading coefficient. The sequence converges to 1. So those terms are getting closer and closer and closer and closer and closer and closer to 1. And they get close to 1 pretty quickly because the bottom is only 1 larger. Okay, so we would say then that the sequence, just to write out a sentence, the sequence, what's the word? Converges, yeah, to 1. Yeah. All right, we don't have to do a whole lot of these. Let's look at this. 1/2, 1/4, 1/8, 1/16, comma, dot, 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 comma, 1 over 2 to the n. What do you think? Converges or diverges? Converges. Okay, let's not even show the analysis there. Let's just say this one converges. Now, once you say it converges, it's nice to see if you can figure out to what does it converge. 0. Yeah, 0. Yeah. Yeah. Okay. Oh, look at this fella. This is 3 plus -1 to the n. We saw this guy yesterday, right? This guy is called an alternator because based upon which n, if it's n or n plus 1 or n minus 1 in the exponent, it's either going to be a -1 or a +1. So if you take the limit as n goes to infinity, what do you think? Very good. That's what it does, right? When in doubt, just list out a few terms. This is the same as when n is 1, you get 3 minus 1 is 2. When n is 2, you get +1, so you get 4. When n is 3, you get -1, so let's go back to 2, 4. Yeah. So that makes it easier to see. So yeah, you can say this one diverges. And again, there's 3 ways it can diverge, right? Diverges to infinity, diverges to -infinity, or diverges by oscillation. Yeah, Mason got it. Yep. Excellent. Okay. Let's jump down here. I'm not gonna do all these. Let's do F. You do it. I'll do it too quietly. You do it quietly, and we'll compare answers. I'm looking at n factorial or n plus 2 factorial, and I see n plus 2 factorial as being bigger, right? So it grows faster. And anytime something grows faster in the bottom, it should go to 0, right? But I mean, that's the intuition. But we also know that if I have something like x cubed over 3x cubed plus 5, the bottom kind of gets bigger faster in that respect too, doesn't it? Because it's always 3 times bigger. And then, oh, by the way, add 5. But we know that one doesn't go to 0. That one goes to 1/3, right? So you got to be careful when they belong to the same family. There's kind of different rules. So for something to be definitive like this, what you'd want to do is see if you can get rid of the factorials, which we've already seen how to do that, right? Which one's bigger, n or n plus 2? N plus 2. So we'll just rewrite the bottom as n plus 2 times n plus 1 times n. Oh, there they are. They're the same. And now you're left with 1 over. And now if you were to distribute the bottom, you would get an n squared in the bottom, right? Which would be the same as like x going to infinity with 1 over x squared. And now we know for sure that that will be 0. Okay. So that's the real litmus test right there. Let's see. Let's do another one. How about this? This is a good one. Oh, I like this one. What say you, Mason? Oh, yeah. Yeah. When in doubt, you can expand it out. When in doubt, expand it out. So if you let n equal 1, you get 0 over 1 times who cares? You get 0 for your first term. When n is 2, you've already done it, you get 1/2. And then you get negative 2/3, 3/4. So good. I'm glad. Okay, let's, yeah. Nice, nice. So there's a difference between the magnitudes converging and the actual sequence converging. If you notice the pattern there, once we get past 0, the signs seem to switch, alternate, right? And the reason they alternate is because you actually have an alternator right there, which is a factor. So when you're multiplying by an alternator, which is either 1 or -1, it's going to change the sign every other positive integer. So with this alone, this one's not oscillating between two fixed values, but it's still oscillating, right?
No, I mean, wait, no.
Well, look at the magnitudes. Because we're taking the limit as n goes to infinity, we can actually take the limit of each factor, right? That's one of the things with the limit we could do. It doesn't have to be a sum. We could take the limit of each piece. So if you take the limit of the alternator separately from the limit of the n-1 over n, this second piece here now, that goes to 1. And 1 times anything is itself. So it reduces down to the same behavior that this has. And we've already seen that this one alternates. So this one, the whole thing does diverge, and we'll say by oscillation. So it doesn't have to oscillate between two fixed values. It either is between two fixed values or between two values that are getting bigger and bigger and bigger. Now, if it was oscillating between two values that got smaller and smaller and smaller, approaching a 0, then it would be 0. Yeah, yeah. So those rules, those properties of limits that we talked about way back in chapter 1 still apply. Yeah. When you see a -1, not quite, because what if this were to the 2n? Yeah, that changes it. Yeah, or 2n plus 1. Yeah. So there are different versions where they're trying to be sneaky, but yeah, the standard alternators are -1 to the n, -1 to the n plus 1, -1 to the n minus 1. These are the same. They just kind of they're both out of step from -1 to the n. And then you have things like cosine of pi n, which is similar to what we were trying to do yesterday with sine, right? If you look at n, when n is 1, you get cosine of pi, which is -1. When n is 2, you get cosine of 2 pi, which is +1. When n is 3, you get 3 pi. So this is kind of a sneaky alternator right here. Sneaky snake in the grass alternator. Okay. But yeah. Just be careful, right? When you assume things. Yeah, because sometimes they will try to be sneaky. But yeah, if you simplified -1 to the 2n, like we have there, that's the same as -1 squared to the nth power, right? Using the rule of exponents. So if you don't realize that 2n is always an even number and a negative number to any even power is always +1, you could just say, oh, if I write it like that, what's -1 squared? That's 1 to the n. And what's 1 to any finite power? 1. So that's always going to be a 1. So it doesn't necessarily change the sign. Okay. Let's do this one together because this is a good review. I don't think we've quite done this yet, but it's a review plus it's an extension. I'm going to take the limit as n goes to infinity of a sub n, and I'm going to write it as 1 plus 1 over n to the infinite power. I'm going to let it equal L for limit. Now, this one's kind of interesting because I'm sorry, I already plugged in. This should still be to the end. My bad. If you plug in on the inside, 1 over n is going to 0, right? And 0 plus 1 then is approaching 1. So that's the inside is approaching 1 from above, right? It's always bigger than 1, but getting smaller towards 1. So it's approaching 1 from above. When you plug in an infinity for n, you get an infinite power. Now, 1 to the infinity power, if it were truly a 1 the whole time, would be 1, right? 1 to any power is 1. But it's never actually a 1 on the inside, right? It's always something a little bit bigger than 1. So this right here, you can't say is equal to 1. This is another indefinite form. So this is going to require, this is the next rung on the L'Hopital's ladder. L'Hopital's rule, okay? So we've learned that if L'Hopital's rule works, if it's this form or plus or minus infinity over infinity form, okay? That's the only 2 forms it works. If we have 0 times infinity, which I think we've seen, which is the product version, we have to make it into one of these by bringing one of those factors to the denominator, okay? But this is the next rung up. This is not multiplication, it's exponentiation. So what we have to do here is use the power of logs. So if you ever have an exponentiation indeterminate form, you're going to need to take the natural log of both sides before you lop it. Take ln of both sides. And why is that going to work? Because natural log is going to allow us to get that n as an exponent out of the exponent. So we get the natural log of L equals, and you can take the limit out front here. The limit as n goes to infinity of the natural log of 1 plus 1 over n to the nth power. And notice I left a little space because now that the natural log is there, where can I put this n? Out front, okay? Boom. Now, if I try to evaluate the limit on the right-hand side by direct substitution, I'm going to get infinity times the natural log of 1. What's the natural log of 1? 0. Oh, so now I've turned it into the multiplicative indeterminate form. 0 times infinity is another indeterminate form. So I'm making progress. I've taken it from exponent indeterminate form to multiplicative. And now all I got to do is bring one of these factors to the bottom. And I don't think I want to mess with bringing the natural log to the bottom. So I'll let him stay in the top. And I'll bring the n to the bottom by calling it 1 over n or n to the negative first, either one. And notice the left side is still a natural log of L. Now use direct substitution to evaluate the limit. Now in the top, you're getting the natural log of 1, which is 0. And on the bottom, what's 1 over infinity approaching? 0. Hey, did we finally get it into one of the 2 required formats for L'Hopital's rule? We did. We did. So now we can lop it. Now, we're not doing logarithmic differentiation here. We're not taking the derivative of both sides. So the left side is still the natural log of L. But we're evaluating the limit by taking the derivative of the top and dividing it by the derivative of the bottom. So remember, the derivative of the natural log of blob is 1 over the blob times the derivative of the blob. Well, the derivative of 1 plus 1 over n is 0 plus, and then 1 over n is really n to the negative first, right? So that becomes negative n to the negative second, chain rule. And in the bottom, it's not the Hody-High rule. In the bottom, what's the derivative of 1 over n? Oh, it's negative n to the negative second. Holy moly smokers. What happens with those 2 factors? They divide out. Boy, don't that convenient. And now if I plug in to what's left, this is all that's left. I get a 1 over 1 plus 1 over infinity is 0. And that equals what? 1. Now, you got to be careful because this would be a great multiple choice question. And guess what answer choice A would be? 1. Well, that's not the answer because 1 is equal to the natural log of L. All we got to do is solve back for L, which is what we originally wanted, by e'ing both sides. So e to the natural log of L is L, and e to the first is E. Oh boy, there it is. E, like is in Euler's number, 2.718. Yeah. Yes. This is actually one of the many definitions of E. This is how E is related to finance. This is continually compounded interest. Continually compounded interest. This is how this is how an interest formula, a general interest formula. Let me just write this because it is kind of interesting. Interest formula. The amount A at any given time is going to be P, your principal amount, your original amount, times 1 plus your interest rate divided by N to the N-th power, where R is your interest rate as a decimal and N is the number of times it's compounded per time T. Okay. The more often something is compounded, the faster the balance builds up, right? So like when the bank is giving you interest in your banking account, they calculate it once a month, which would be 12 times a year. When your credit card is calculating the interest because you have to pay them, they're doing it daily at least, okay? Because the more often you compound, the faster it builds up. So in this case, if N is the number of times we compound it, if you let N go to infinity, and there's a couple of substitutions we'd have to do in here to make it look right, it turns into this equation. As N goes to infinity, A becomes PE to the RT. It turns into the PERT equation. What's another name for the PERT equation? The sect equation. Very good. Very good. It's just in a different context, right? We call it K instead of R. We call it C instead of P. Yeah. So pretty interesting. So this is another reason why Euler's number is sometimes called the banker's number, although it starts with E, not a B. But yeah, that's one of the definitions of E. So anyway, this sequence converges to E. And now you've seen, we're going to backtrack and maybe do another. There's a couple of other indeterminate forms. I said indefinite form, sorry. It's indeterminate form. Still recovering a little bit. It's kind of down into the lower, I think it's below the esophageal sphincter at this point. Heating up. All right. Well, there's a couple of other versions, but anytime it's in the exponential form, the other two indeterminate forms, you're going to accomplish evaluating it the same way using logs. Okay. So anyway, there you go. All right. We skipped a few of those, but that's fine. All right. Let's look at example 4. I mentioned yesterday that a lot of times we have to come up with the nth term because it's not given. Bless you. So 3, 8, 13, 18. Does this sequence converge or diverge? What verge? Yeah, it appears to be getting bigger, right? So that would be diverges, right? This diverges to infinity, okay? But sometimes we may want to know what the rule of sequence or the nth term is, either to verify it, right? Because intuition can kind of sometimes betray us when we're talking about infinity. There's going to be a lot of paradoxes along the way. Or we need it for something else, like we want to be able to integrate or take the derivative of, okay? So remember, we're starting with n equaling 1, the set of natural numbers. Start with, how can I write a formula that generates those numbers based on power or values of n? Where this would be a sub 1, in other words, this would be a sub 2, a sub 3, a sub 4. Do you see a pattern there? Can you predict the next number? 23, right? And the one after that would be 28, right? So this one, all we're doing to get to the next term is adding 5, plus 5, plus 5, plus 5, plus 5. We call this an arithmetic sequence. You spell it the same way you spell arithmetic, but you say it as an adjective with an accent on the E, arithmetic sequence, not an arithmetic sequence, right? So arithmetic sequences are those that only, to get to the next term, you add or subtract. Okay, you add or subtract to get the next term. Well, think about it. If I want to write a rule that generates it, plus 5 plus 5 plus 5 plus 5. If we wanted to add 5 over and over and over again, isn't there an abbreviated way to do repeated addition? Multiplication. Very good. So arithmetic sequences, which are add or subtract to get the next term, turn into multiplication or linear rules of sequence. Okay. So this should equal, how can we generate it? Well, let's see. If we could generate the first term, it looks like if I am going to be adding 5 each time, it should be 5n, right? Yeah, 5n. Plus 5 twice is 5 times 2. Plus 5 plus 5 plus 5 3 times is 5 times 3. So if you know what that common difference is, that's what we call it. To figure out that number, instead of saying, what do I add? You can always do right minus left, right? 8 minus 3 is 5. 13 minus 8 is 5. 18 minus 3. That's your common difference, we call that. The common difference is, in general, a sub n minus 1 minus a sub n. I'm sorry, a sub n plus 1. All right. And then all you have to do is adjust. Just adjust. When you plug in an n equals 1, you get 5. What would I have to do to turn that into a 3? Subtract 2. Yeah. And then try it out for the next one. When n is 2, I get 10 minus 2, that's 8. When it's 3, I get 15 minus 2, it's 13. Boom. Got it. Okay. So repeated arithmetic, addition, subtraction, sorry, turns into multiplication, which is going to be a linear rule of sequence. And now you can easily see that the limit as n goes to infinity of 5n minus 2 is infinity, right? 5 times infinity minus 2. Yeah, okay, cool. Cool beans. All right, how about this fella? First of all, converge or diverge? The sequence diverges, right? Because it's oscillating, looks like. Yeah, okay. So what do we got here? Let's see. If I go from 5 to negative 15, I'm subtracting 20. Does that work for the next term? Negative 15? No. So no. Hey, well, if it doesn't work by subtracting to get the common difference, what about trying division? Right? What's negative 15 divided by 5? Negative 3. What's 45 divided by negative 15? Negative 3. Yeah. So on and so forth. So we call this, these have a common, we call it a common ratio. You multiply or divide to get the next term. So instead of a common difference, there's a common ratio. We call these geometric sequences. And these are actually more important to us than the arithmetic. All right, so we could say, if we want to go forward, this is times negative 3 times negative 3 times negative 3. That's supposed to be a multiplication symbol. I'll put an asterisk there because it looks like an X. Hey, what do we call repeated multiplication? Exponentiation, right? Exponentiation. So geometric sequences are the same as exponential sequences, but that's not their formal name. Okay, but they do turn into exponential. So what would the common base be? Well, it would be negative 3 to the nth power, right? Now notice we can't have negative bases for exponential functions when the domain is all real numbers. It doesn't work, because negative 3 to the first power is negative 3, and negative 3 squared is 9. But what's negative 3 to the 1/2 power? Imaginary, right? It's the square root of negative 3. So if we're talking about domains of all real numbers, can't have a negative base. But hey, what's our domain? natural numbers, right? 1, 2, 3, 4, 5, 6, 7. And that we could do that all day long. So we can actually have negative bases now. So let's say that a sub n equals that, and then do any adjustments if we need it. When n is 1, we get 9. Well, that's not right. 5. How can we get from a 9 to a 5? What's that? -4. Okay, so that'll work for the first term. Let's see if it works. Oh, to the first. I'm an idiot. I was looking at the second. What was I looking at? I said -3 squared. That's why. Sorry. You have to be extra forgiving today. My body is wrenching inside. Yeah. Let's see. -3 to the first would be -3. So this has to be a sub 1. And it's not. So how do I turn a -3 into a 5? Here's another thing you can do. Watch this. If I could, let's see. Does anyone know off the top of their head? Does anyone see the pattern?
No, I don't. It's opposite of the normal like flip.
Opposite of the normal
Never
flip?
mind, I'm stupid.
No. No, I think.
The normal repeater, it starts with negative, but this one starts with positive, so you have to multiply n by -1.
I see what you, yes. Yeah, that's the first thing. You're noticing at the sign. When n is 1, I'm going to get a negative number, right? So I'm going to have to put an n plus 1 or an n minus 1. No, that's exactly right. That's part of it. Yeah. No, that's very good. That'll take care. No. That's excellent. That's why we're doing these, right? We're having these quote unquote conversations. That'll take care of the plus or minus. Okay. Now I need to focus on the magnitude. When n is 1, I need to get a 5, but right now I'm getting a +3. How can I get rid of the 3? Let's talk about that first. How could I get rid of the unwanted 3? Help me out, everybody. Well, just think about like when we were integrating. If we had an unwanted factor of 3, we have a correction of a 1/3. And now that would give me a 1. How do I turn that into a factor of 5? Multiply by 5. So let's see if this works. That gives me 5/3 times -3 to the n plus first power. Let's see if that does the trick. Let's expand it out. When n equals 1, we plug it in and we get 1 plus 1 is 2. Oh, we get an unwanted 9, don't we? Because now we have an n plus 1. So instead of a correction of a 3, I need a correction of a 9. Oh, yeah. Is there a better way? I'll show you a better way here in a second. Plug in a 1 now. Let's see if it fix this correction. 1 plus 1 is 2. -3 squared is 9. 9 divided by 9 is 1, and 1 times 5 is 5. Boom, we got the first term. It must be right all the way down the line now. And, I mean, in your head, you could be like, I know it's going to work because we've made the necessary corrections. Let's try for one more, right? When n is 2, what do we get? 2 plus 1 is 3. -3 to the third is -27. -27 divided by 9 is -3. -3 times 5 is -15. Oh, Merry Christmas. We did it. Yeah, it's going to work the rest of the way. Okay. That's a lot of this chapter has a lot of this in it. So yeah, it's just trial and error, guess and check, look for the pattern. Now there is a slightly easier way. If it's geometric, and we're going to see a lot of geometric, if you could turn your first term into a 1, it makes life easier. So let's factor out a 5, and this is kind of informal notation, but let's factor out a 5 and see what all the rest of the terms end up being. Now it's a 1, and then it's a -3, and then it's a 9, which is -3. Yeah, well, let's call it a 9. We'll call it a 9, and then it's going to be a 27, -27, so on and so forth. Okay, now that's going to be a little bit easier because now I already know it's times -3 times -3. Let's see if we can write these residuals now as powers of that common ratio. One is -3 to the 0, right? Which is kind of what Braden was saying. The next one is -3 to the first. 9 is -3 squared. 27 is -3 cubed. And now all we have to do is make our adjustment. All right. So a sub n, there is going to be a 5 there. And now it's going to be -3. But if I just put an n there, that's not going to work. I want, when n is 1, I want the exponent to be 0. So what do I do to the exponent just to make it one smaller? N minus 1. Yeah. So n minus 1 and n plus 1, they have the exact same effect on the alternator. But sometimes we may want to make the number smaller by doing n minus 1 rather than making it bigger. This is right here. This is actually equivalent to this one here. Which one is correct? They're both correct because they're both going to generate the exact same sequence. Now, you can easily show that this one, I think it's probably easier to show that this one is equivalent to the one we came up with because I can use that little technique. -3 to the n plus 1 is the same as -3 to the n times -3 to the first, right? I hope. -3 to the n plus 1. Does this work? Yeah, this should work, right? Yeah.
Should work.
1 plus 1 is 0. Oh, hey, did we get the sign right? Is that I didn't check the sign over here, did I? If I plug in a 1, I get 0, 1. If I plug in a 2, oh, that works. Yeah. Yeah, if I do this over here, -3, the first is -3. One of these is off. One of these is off. What should happen here is this one should divide out with this one, and we're just left with 5 times -3 to the n. Oh, I gotta factor out twice. Yeah, I gotta factor out another one. Let's do this. Let's rob Peter to pay Paul. See that? I took another -3 out of the exponent. Ah, that's gonna work. Now what's -3 times -3? That 9 divides out with this 9, and we're left with -5, -3 to the n minus 1. Okay, they are the same. Okay, so that's what was wrong. It was me. Which way was easier? Well, this method here is a little bit more systematic. A little more systematic. We're going to see geometric quite a bit more, so you'll get more comfortable with that later on. All right, I think that's all I'm going to do for that. Okay, you get the idea. Arithmetic is a common difference, add or subtract to get the next one. Oh, and by the way, to find that common ratio, we're going to give that a name. We're going to call that R, and it's going to be a sub n plus 1 divided by a sub n. A sub n plus 1 is the term that is 1 after the nth term. It's the next term. So you take the one on the right divided by the one on the left. We're going to call that R. The common difference over here is actually called D, but we don't really need to know that. Okay. Geometric are the same as exponential. All right, but they're functions of n instead of functions of x. Whew. All right, let me give you one to try on your own, right? Because I know you're like, what the? Okay, how about this? How about this? Let's just do an easy one. 4, 8, 16, 32, ... All right, go ahead and write the nth term for that. I probably started you off with one that was too hard. But it was Grayson's birthday, and I wanted it to be special. All three get the same thing? It must be right. Because in the land of democracy, it belongs to those who actually vote. I saw many of y'all doing like common differences first. 8 minus 4 is 4. 16 minus 8 is not 4. So it's not going to be arithmetic. 32 minus 16 is 16. Now, watch this. There's still hope. No, that would be quadratic. Okay, so it's not arithmetic. I was trying to teach you if it was a quadratic sequence. I may return to that. So if it's not arithmetic, maybe it's geometric. 8 divided by 4 is 2. 16 divided by 8 is 2. 32 divided by 16 is 2. Ah, yeah. So I know it's going to be times 2 times 2 times 2. So it is going to be geometric, right? Which means it's going to be exponential and the base should be 2. The question is there an A out? Is there like an initial value out front? And is it n plus 1 and minus 1? Is there an alternator? Well, again, you could do it like this. You could say it's 4 and then divide it out. 1, 2, 4, sorry. 8. Yeah, I'm twitching here. Dot, 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 close brackets, close braces. Yeah, and then this would be you already know your common ratios too. So again, this is 2 to the 0, 2 to the first, 2 to the second, 2 to the third. So now you could say, okay, a sub n is going to be 4 times 2 to the what? N minus 1. Yeah, because I need that to correspond with 0 when n is 1. So I subtract 1. And there it is. Yeah, that's probably the easiest way to do it. So you can write it like that, or you can write it like this. Or you can actually write it like we have, 4, 8, 16, and then put the nth term, of course. Okay, there you go. So those all mean the same thing. Now, that's probably a better one to start with. 2 to the n plus 1. Let's see. Are there other versions of it? Yes, there's going to be a lot of different versions of it. 4 is 2 squared, and this is 2 to the n minus 1. So if you add exponents, because the bases are the same now, 2 minus 1 is 1. So that also works. Yeah, boom. Very good. You could do it this way. You could say 4 is 2 times 2 times 2 to the n minus 1, and just rob 1 Peter to pay 1 Paul instead of 2 Peters to pay 2 Pauls, and leave the 2 out front, and now say it's 2 times 2 to the n. Those all are the exact same. Why are they the exact same? Because they all generate the exact same, rhymes with dequence and starts with S. Sequence. That's right. No, that's delinquents. No, that's different. There's too many syllables. Delinquents. No, actually, it's the same. It's 2 syllables. Clap it out. Delinquent. All right. Okay, so in the next 4 minutes, I'm going to at least define to you what a series is, because sequences are one thing, but this section from here on out is really about infinite series. Okay, here's the basic definition. A series is the sum of the terms in the sequence. That's it. A series is the sum of the terms in the sequence. So really, instead of separating them with commas, we're just separating them, guess what, with addition symbols. Right. And now the bigger question becomes, does the series converge or diverge? Does the sum of infinitely many terms get infinitely large, infinitely small, or does the sum taper off towards a finite value? That's a very different question. Can it be possible to continue to add something that's positive over and over and over again forever and ever and ever, and still have it converge to an actual number and not get infinitely large? The stepping thing. Well, that would be a sequence because I'm just measuring my distance from the door. I would have to add up the total of.
It never gets bigger.
That one's not real intuitive. If I add up the total distance I'm walking towards the door, I have shown you one. The 2 pennies. Yes, because this is a series. You have 1 cent plus another half of a cent, okay, plus another fourth of a cent, plus another eighth of a cent, plus, and you can visually see, right? I know that. This series converges to 2. Yeah, that series converges to 2. And it's easy to see why. Now, look at this. What if I went 1 plus 1/2, but now plus 1/3, plus 1/4, plus 1/5, plus 1/6, plus 1/7, plus 1/8. Notice the terms that I've already added that I say converge are in this sum, but it's a little bit bigger. It's got a few extra terms, but they're small. What do you think this happens to this series? No, this one diverges to infinity. And that's a good cliffhanger for the week, right? But how? If the first by the same, but really, if you think about it, I mean, what's to say that it can't? But I guess I'll think about it all weekend long. No, yeah, no, right? Maybe, but if you possibly, then can you know? What if perhaps may? Yeah, it's right on the tip of my, what do you call it? Maybe, yeah, but there, it's just different, same. Oh, one goes to 2 and one goes to infinity. That's bizarre, right? There's your cliffhanger for the week, okay? Here's a little hint. It has to do with how fast the terms go to 0. That's got a lot to do with it.